Hidden around the Milky Way are some of the smallest and faintest galaxies ever found. They hold only a few ancient stars, almost no gas, and just enough light to avoid vanishing completely into the dark. Yet these nearly invisible companions may preserve some of the oldest clues about how galaxies first began. In tonight's journey, the view turns toward these quiet cosmic relics. If this kind of deep space mystery belongs on the channel, please like the video, subscribe, and settle in. Astronomers use the name local group for the small galactic neighborhood that holds the Milky Way and its nearest companions. It is not a crowded city of shining spirals and giant swarms of stars. It is a loose and quiet gathering, spread across a volume of space that reaches for several million light years. Within that wide reach, gravity ties together more than 50 known galaxies, and perhaps more once the faintest members are fully counted. Two great spirals dominate the group. One is the Milky Way. The other is Andromeda. Triangulum follows as a smaller spiral, while most of the remaining members are dwarf galaxies, systems far less massive and far less bright than the major pair. Around this calm arrangement, the wider universe continues in every direction, with more distant groups, clusters, sheets, and voids shaping the larger setting in which the local group rests. From this outer view, the Milky Way does not stand alone. It shares its region with neighbours that differ enormously in size, brightness, and structure. Some galaxies in the local group are broad and obvious. Others are modest clouds of stars with no grand outline at all. A few can be seen with the unaided eye under dark skies, but most cannot. Their light is too weak, too spread out, or too far away to rise clearly from the background. The local group therefore appears simple only from a distance. In reality, it is made of many small systems whose presence becomes clear only through patient surveys and careful measurement. This is the setting in which ultra-faint galaxies take their place. They are not distant curiosities far beyond the Milky Way. They belong to the nearest galactic environment and are woven into the same gravitational neighborhood as the galaxy itself. The frontier of this neighborhood is not marked by a wall, it fades outward. At larger distances from the Milky Way and Andromeda, the pull of each giant galaxy weakens, while the shared gravity of the group blends into the wider flow of nearby space. Some galaxies near the edge remain bound to the local group. Others lie just beyond it and drift according to a broader pattern shaped by surrounding matter and vast emptier regions. The nearby universe is not arranged like beads on a string. It forms a web, with matter gathered into strands, flattened regions, and denser knots, separated by great dark intervals where galaxies are scarce. The local group occupies one small part of this larger design. Even in the immediate cosmic vicinity of the Milky Way, the landscape is already structured by forces acting over enormous distances. Within the local group itself, the great spirals hold the eye, but they do not tell the whole story. The smallest galaxies are the most numerous class. Dwarf galaxies may contain from many millions of stars down to only a few thousand visible ones in the faintest known cases. This range is important because it shows that a galaxy does not need to be large or bright to count as a true galactic system. In the local group, smallness is ordinary. The Magellanic Clouds, visible from southern latitudes, are famous examples of dwarf companions, bright enough to stand out. Yet they are only the luminous edge of a much broader population. Beneath them lies a quieter tier of dwarf galaxies so dim that they emerge only after long exposures, star counts, and comparisons across wide regions of sky. The ultra-faint galaxies belong to this hidden tier. Seen from the outer scale of the group, these systems resemble almost nothing at all. They do not announce themselves with spiral arms, bright cores, or rich clouds of gas lit by new stars. Many appear instead as the thinnest excess of ancient starlight, a slight gathering of points that would pass unnoticed without statistical care. Some known examples near the Milky Way contain only several thousand stars, and newly reported systems may contain far fewer visible stars than even that. At the broad scale of the local group, such objects seem close to disappearance, yet their very existence matters. They show that galaxy formation extends far downward in size and brightness, into a regime where the word galaxy begins to approach its practical limit. This wide setting also explains why the census of the Milky Way's smallest companions remains incomplete. The local group is near in cosmic terms, but nearness does not make every member easy to detect. A dim system can hide because it lies against a busy field of foreground stars. It can hide because its stars are scattered thinly across the sky. It can hide because only part of the sky has been surveyed deeply enough to reveal it. It can also hide because some objects sit near the uncertain boundary between a galaxy and a star cluster, with too little visible matter to make classification simple. In the outer neighbourhood of the Milky Way, discovery is therefore not just a matter of looking farther. It is a matter of seeing more carefully inside what already surrounds the galaxy. This is one reason the number of known satellites continues to change. New searches in recent years suggest that the Milky Way may be accompanied by many more ultra-faint systems than are presently catalogued. Some estimates indicate that dozens of hidden companions remain undetected, and perhaps close to 100 more satellites of varying brightness await discovery around the Milky Way. Such estimates do not mean that astronomers have already seen them all and merely failed to count. They mean that the observed sample appears incomplete when compared with survey limits and with models of how many small systems should survive around a galaxy like the Milky Way. From the outer local group perspective, the Milky Way may therefore sit inside a much richer retinue than the current map plainly shows. At this broad frontier, the hidden galaxies around the Milky Way are best understood not as isolated oddities, but as the faint end of a nearby population. They occupy the same neighbourhood as the major members of the local group, though they contribute almost none of its visible grandeur. Their importance lies in their quiet persistence. They remain present at the edge of detectability, preserving a record that brighter systems can blur with later growth and activity. In this wide setting, they appear as part of a sparse galactic archipelago, many small islands of starlight, some obvious, some barely there, all sharing one local sea of gravity. Beyond the bright disk of the Milky Way, beyond the dense band of stars that gives the galaxy its familiar form, the outer halo opens as a broad and quiet region. It does not resemble the central bulge, where stars crowd together, and it does not resemble the disk, where spiral structure, gas, and dust define the main visible body of the galaxy. The halo is more diffuse and far less obvious. It surrounds the Milky Way in a loose, nearly spherical envelope. In this far region, stars become scarce, distances widen, and the sense of structure changes. Instead of a shining plain, there is a dim volume of space populated by ancient remnants, remote star clusters, thin stellar streams, and small companion systems moving under the galaxy's pull. Astronomers often separate the Milky Way into parts by both shape and history. The disk is flat and rich in ongoing activity. The halo is extended and comparatively quiet. Even within the halo, the inner and outer parts do not seem identical. Observations suggest that the halo preserves a layered record of growth, with material added over long spans of time as smaller systems are drawn inward and absorbed. The outer halo is therefore not simply empty space around the galaxy. It is a repository of faint evidence. It holds stars that are widely scattered, not concentrated into a bright field, and it preserves the remains of former companions whose identities have partly dissolved into the larger system. In this sense, the outer halo is less a border than a long zone of transition, where the Milky Way thins into its own history. This region is vast. The visible stellar halo extends to roughly 300,000 light-years across, far beyond the brighter disk, while the Milky Way's broader gravitational reach extends much farther still. Yet size alone does not make the outer halo prominent. Its defining feature is low density. A person imagining this region as a thick cloud of stars would imagine it wrongly. The stars are too far apart, the light too weak, and the structure too thin for that. Much of the outer halo is dark in the ordinary sense, not because nothing is present, but because what is present emits so little light per unit area that the region offers almost no grand outline to the eye. It is a place understood by careful mapping rather than by direct impression. This thinness matters because hidden ultra-faint galaxies inhabit the same broad environment. They do not orbit within the crowded disk, where dust, gas, and huge numbers of foreground stars would overwhelm their weak signatures. They are found instead in the halo, especially in its farther reaches, where the Milky Way's visible body loosens and small satellites can persist at large distances from the centre. Some known ultra-faint dwarfs lie tens of thousands of light-years from Earth. Others lie hundreds of thousands of light-years away, still within the Milky Way's broad halo. Leo IV, for example, resides about 500,000 light-years from Earth in the halo of the Milky Way. At such distances, the galaxy is no longer a bright surrounding field but a dominant centre seen from afar, holding its minor companions in a wide gravitational domain. The outer halo is also the region in which the Milky Way reveals how it has grown. Streams of stars arc through this volume as traces of older systems pulled apart by gravity. Remote clusters and detached stellar populations suggest repeated accretion, the gradual growth of a larger galaxy through the capture of smaller ones. Studies of halo stars support this picture. Their motions and ages indicate that the halo does not form all at once from one event. It accumulates in stages, in the outskirts especially. Ancient stars from long ago dwarf galaxies appear to settle into a sparse envelope around the Milky Way. The outer halo therefore serves as a kind of quiet archive. It does not preserve former structures intact, but it keeps enough of their material to show that the galaxy expands by addition as well as by internal evolution. For ultra-faint galaxies, this environment is both shelter and challenge. It shelters them in the sense that the halo is spacious. Small systems can orbit there without immediate destruction, sometimes for billions of years. The outer halo allows wide paths, long periods, and relatively weak direct interaction compared with the denser inner regions nearer the galactic centre. At the same time, the halo makes them difficult to detect, even though the background is less confused than in the disk. These satellites are extremely dim and often spread thinly across the sky. A tiny galaxy in the outer halo may appear only as a slight clustering of faint stars. Its light does not rise as a bright patch. Its presence has to be inferred from patient surveys, stellar motions, and the careful separation of member stars from the foreground stars of the Milky Way. This is why the outer halo often feels richer in hidden structure than in visible form. It contains more than it first appears to contain. New discoveries repeatedly reveal that objects once thought absent are merely difficult to distinguish from the surrounding field. Some systems occupy a troubling middle ground between an ultra-faint galaxy and a star cluster. In such cases, the outer halo is not only a location but also a testing ground for classification. Here the smallest bound stellar systems live near the practical threshold of detectability and near the conceptual threshold of what astronomers are willing to call a galaxy. The faintest satellites of the Milky Way push both boundaries at once. The outer halo therefore frames the search in a precise way. It is the broad, dim, ancient envelope around the galaxy where the smallest companions linger, where the record of accretion remains only partly mixed, and where the Milky Way's true surrounding population is still being counted. It is neither empty nor fully known. It is a sparse realm of weak light, long orbits, and unfinished inventory. Around the Milky Way, the hidden ultra-faint galaxies belong first to this environment before they belong to any narrower category. They live in the galaxy's far envelope, where the visible body has thinned, where the past is lightly scattered through space, and where even nearby galaxies can remain concealed for a very long time. Across the outer halo, the Milky Way's satellite population does not present itself as a smooth and even shell. It is not arranged with equal density in every direction, and it is not revealed to observers with equal clarity across the sky. From a distance, one might imagine that small companion galaxies should circle the Milky Way in a simple spherical swarm, spaced with rough fairness around the galactic center. The real pattern is quieter and less regular. Some regions of sky contain several known satellites in a relatively limited area. Other regions appear sparse. Some companions stand far from the Milky Way's center, while others lie much closer in, even before the faintest systems are considered. The satellite realm looks scattered rather than uniform. Part of this scattered appearance reflects the way galaxies actually gather and move. The Milky Way does not grow in perfect symmetry. Small systems fall inward from different directions over long spans of time, often as members of larger associations. A dwarf galaxy can bring smaller companions with it. A nearby massive satellite can influence where related faint systems are found. The Large Magellanic Cloud is especially important in this regard. It is not merely one bright companion among many. It is a substantial satellite in its own right, and evidence suggests that some ultra-faint galaxies are associated with it. This means that the angular pattern of known satellites on the sky is shaped in part by group infall, where several small systems arrive along related paths rather than from wholly independent directions. Because of this, the realm of satellites can look lopsided. It may appear richer in some broad sectors of the sky than in others. Recent studies of the Milky Way satellite census describe a mild anisotropy, meaning that the distribution is not perfectly the same in every direction. That does not imply a rigid or mysterious geometric order. It means only that the sky map of satellites shows some unevenness beyond what a perfectly balanced sphere would suggest. In current work, part of this mild imbalance is attributed to the clustering of satellites associated with the Magellanic System. The satellite population therefore carries a memory of shared motion and shared origin. The pattern is not random scatter alone, even if it seems irregular at first glance. At the same time, the apparent distribution of satellites is shaped by the position from which the Milky Way is observed. Earth lies inside the galaxy's disk, not outside it. That fact matters deeply. Looking outward from within the disk means looking through foreground stars, dust, and changing levels of sky confusion. In some directions, especially near the galactic plane, the field is crowded and the background is difficult. In other directions, Especially at high galactic latitude, the foreground is thinner and faint systems are easier to pick apart. The sky is therefore not equally transparent to the search. A hidden galaxy made of only a small number of dim stars is much easier to miss when it lies behind a thick foreground of brighter Milky Way stars. This creates an important distinction between where satellites truly are and where they are easiest to recognize. The two are not identical. A region with many discoveries may be a region with many satellites, but it may also be a region where the conditions for detection are better. A blanker region of sky may contain fewer satellites, but it may also conceal some of the faintest ones behind difficult foregrounds, or in areas not yet searched with equal depth. The scattered satellite realm is therefore a map of both nature and visibility. It combines the actual arrangement of the Milky Way's companions with the uneven clarity of the sky through which they are sought. The faintest systems intensify this problem. Bright satellites announce themselves by sheer presence. Their stars are numerous enough, or their structure broad enough, that their identity becomes visible with less uncertainty. Ultra-faint galaxies do not behave this way. They can consist of so few detectable stars that their existence depends on a small excess of points in one patch of sky over what would normally be expected. In some cases, the visible membership is so small that the system stands near the boundary between a tiny galaxy and an unusually sparse cluster of stars. When such an object is placed against a complicated foreground, or when it lies in a region where the background field varies, its detection becomes much less secure. Across the sky, then, the faintest companions are not only scattered in place, they are scattered in recognizability. This is one reason why the Milky Way's satellite system has long inspired debate about apparent alignments and patterns. Some studies emphasize that satellites seem to gather in flattened or directional arrangements rather than in a fully isotropic cloud. Other work shows that parts of this appearance can arise from the detailed radial layout of the satellites, from temporary alignments, and from the incompleteness of the observed sample. The broad lesson is not that the satellites form a neat and lasting plane that fully defines the system. The lesson is that irregularity must be interpreted with care. A small and incomplete sample can look more orderly, or more puzzling, than the full hidden population truly is. The scattered realm invites caution because every observed pattern is filtered through limited discovery. Even so, the sky distribution of satellites is not meaningless. It reveals that the Milky Way's outer population has a history. Companions do not enter the halo in a timeless drizzle from all directions. They arrive through cosmic structure, through filaments, associations, and repeated episodes of capture. Some remain intact, some dissolve, some pass close to the galaxy and are altered. Others remain farther out, still preserving a quieter orbital life. The pattern across the sky therefore records both the Milky Way's growth and the present difficulty of seeing its faintest neighbours. The scattered arrangement is real, but it is not fully exposed. Within this realm, the ultra-faint galaxies occupy the hardest positions to judge. They are the least numerous in visible stars, the least forgiving of foreground confusion, and the most sensitive to where attention has been directed. Their discovery map remains patchy, because their nature is patchy at the edge of vision. They gather where history places them, and they disappear where weak light meets difficult sky. Around the Milky Way, the satellite realm is therefore not a clean ring of companions. It is an uneven celestial territory, shaped by infall, by association, by perspective, and by concealment. In that scattered territory, the smallest galaxies remain present but only partly revealed. The sky above the Milky Way is not searched all at once with equal depth. equal clarity, or equal method. It is opened in pieces for the hidden ultra-faint galaxies around the Milky Way. This matters as much as their actual presence in space. A galaxy may exist in the halo for billions of years and still remain absent from the catalogue simply because the right patch of sky has not yet been examined in the right way. The search therefore proceeds through windows rather than through a complete unveiling. Each survey opens a different window. Some are wide and shallow, some are narrow and deep, some favour the north, some the south, and some avoid the densest parts of the galactic plane. The resulting view is real, but it is partial by design. This patchwork becomes easier to understand when the sky is imagined not as one continuous canvas, but as a set of overlapping maps. Modern astronomy has transformed the search for faint satellites through digital, wide-field imaging. Earlier eras discovered the brighter companions first, the ones that could stand out with less subtlety. After the turn of the century, large digital surveys began to change the picture quickly. The Sloan Digital Sky Survey opens a broad northern window and reveals many previously unseen faint companions. Later, work with Pan-STARRS, the Dark Energy Survey, and Delve expands the search into other regions and pushes the census downward in brightness and upward in completeness. The catalogue grows not because the galaxies suddenly appear, but because the sky is being sampled with better tools and broader coverage. Yet even now, the search remains incomplete. Some of the best recent census work combines DES, Delve, and Pan-STARRS into one large footprint, but even that footprint excludes parts of the sky. Regions near low galactic latitude are often left out because the foreground becomes too crowded. Areas near other stellar systems may also be avoided because the local background becomes difficult to model cleanly. Some fields simply lack survey coverage deep enough to support a uniform search. In such maps, the excluded zones are not empty in a physical sense. They are observational blanks, places where the window is clouded, narrowed, or not yet opened fully. This distinction is essential. The hidden population is shaped partly by where galaxies are, and partly by where the view remains usable. A survey window is defined by more than geography. It is also defined by depth. Depth means how faint an object can be detected under the conditions of the data. A deeper survey records dimmer stars and therefore allows a small satellite to be recognized at larger distance or lower luminosity. A shallower survey may still recover brighter companions while missing the faintest ones entirely. This is why the same kind of object can be visible in one dataset and invisible in another. A tiny nearby system can be detected because its stars are bright enough and numerous enough to stand apart. The same kind of system placed farther out in the halo may disappear from the same survey window. In this way, depth does not merely sharpen the image, it changes the reachable population. The search also depends on what exactly is being detected. Many ultra-faint satellites are not first seen as smooth glowing patches. They are found as resolved collections of stars. The survey must therefore measure individual stars accurately across a large field, then identify a slight concentration whose stars share a plausible colour and brightness pattern for a common distance and age. This makes the search statistical. Astronomers are not simply staring at a photograph and seeing a galaxy outlined against darkness. They are counting, sorting, and comparing stars across many parts of the sky. A survey window is therefore also an analytical window. It depends on the precision of the catalogue, the reliability of the star-galaxy separation, and the algorithm used to notice a weak overdensity in a noisy field. Foreground conditions can widen or narrow that analytical window, Dust dims and reddens light. Dense foreground star fields create confusion. Changes in observing conditions across a survey footprint can alter the local ability to detect faint stellar groupings, even within one survey. Some patches of sky are easier than others. A galaxy placed in a clean, high-latitude field may stand out. The same galaxy projected against a richer foreground may blur into the background. The sky window is therefore never a simple shape cut on a sphere. It is uneven in quality from place to place. It has clearer panes and murkier panes, even when the formal footprint says that a region has been covered. This is why astronomers speak so carefully about selection effects. A selection effect is a bias introduced by the way objects are found. In the case of Milky Way satellites, it means that the observed sample is filtered by survey design. Bright, compact. Nearby systems are easier to recover. Faint, diffuse, distant, or foreground confused systems are harder. A proper census must therefore estimate not only what has been found, but also what would have been findable under the actual conditions of the search. Recent work does this by simulating artificial satellites and inserting them into survey data to test recovery rates. Such efforts treat the survey window as a measured instrument rather than as a simple yes or no view. The question is not merely whether a survey looks at the sky. The question is what kinds of satellites that survey can realistically notice. Different surveys also reveal different kinds of opportunity. DES proves especially powerful in the southern sky. Pan-STARRS strengthens the northern and intermediate view. DELVE adds deeper and more refined coverage in important regions. Gaia contributes another kind of window by measuring stellar motions across the sky, helping to distinguish coherent systems from unrelated foreground stars, and even helping reveal exceptionally diffuse companions that had escaped older imaging searches. Together, these efforts do not create a complete map, but they do produce a layered one, in which each window corrects or extends the others. The result is a satellite census that is always provisional. It reflects the current union of footprints, depths, methods, and exclusions. Around the Milky Way, hidden ultra-faint galaxies are discovered through these openings one by one, or in small groups, as the searched sky becomes broader and cleaner. The realm itself does not change quickly. The view of it does. In this section, the Milky Way's hidden companions appear not yet as individual structures of light, but as inhabitants of an uneven observational landscape. They enter knowledge through surveyed sky windows, and those windows remain incomplete, selective, and slowly widening across the dark. The hidden ultra-faint galaxies around the Milky Way remain concealed not mainly because they are the farthest objects in the halo, but because their light is almost too weak to separate from the sky itself. This weakness is best understood through surface brightness. Surface brightness means the amount of light spread across a given area of sky. A galaxy can contain real stars and still appear nearly invisible if those stars are distributed so thinly that the combined glow never rises much above the background. In this sense, visibility is not simply a matter of total light. It is a matter of concentration. A modest amount of light gathered tightly can stand out clearly. The same light spread loosely can fade into near absence. This is why some ultra-faint galaxies remain hidden, even though they are part of the Milky Way's own outer realm. A bright galaxy at a much greater distance may be easier to detect because its light is dense and well organized. An ultra-faint dwarf in the halo may be far closer and still be harder to see because its stars are so few and because their light is scattered across a relatively large patch of sky. The eye, and even the telescope, do not immediately register such a system as a glowing object. It may leave no obvious misty shape. It may instead resemble an almost ordinary field of stars, with only the faintest increase in number from one place to the next. For many of these systems, the background sky is the main obstacle. The night sky is never truly black in an observational sense. It contains air glow, scattered light, unresolved distant sources, instrumental noise, and above all, the countless foreground stars of the Milky Way itself. Against that background, a very low surface brightness galaxy has little power to distinguish itself. In review work on ultra-faint dwarfs, astronomers note that many such galaxies are discovered not because their smooth light profile is seen directly, but because they appear as overdensities of resolved stars whose surface brightness lies below the sky level. This point is crucial. The galaxy is not invisible because it emits no light. It is invisible because its light is too diluted to emerge as a coherent luminous patch. The effect becomes stronger as a galaxy grows fainter and more diffuse. A system with only a few thousand stars, or fewer visible ones in discovery data, does not possess enough stellar content to form a bright body. If those stars are old and dim, the combined light weakens further. If they are spread over tens or hundreds of light years, their contribution per unit area falls again. The result is an object that may have a measurable total luminosity, but almost no visual presence. It becomes a galaxy of subtraction, recognized by what slightly exceeds the expected background rather than by what declares itself plainly. In the halo around the Milky Way, this is often the practical meaning of hidden light. This weak light also explains why discovery images can be misleading. A famous bright spiral galaxy looks richer and more obvious in a single view because billions of stars create a concentrated luminous structure. An ultra-faint dwarf does not. In shallow imaging, it may not look like a galaxy at all. There may be no visible center and no strongly marked boundary. Only when stars are counted carefully, and only when their colors and brightnesses suggest a common distance and age, does the object begin to separate from the surrounding field. The light of the system is therefore not read in one glance. It is assembled analytically from many small signals. A hidden dwarf galaxy is less like a lantern seen in the dark and more like a pattern slowly emerging from noise. This is also why astronomers sometimes describe such systems as ghostly. The word is useful only if it is understood precisely. It does not mean unreal. It means that the galaxies have so little visible matter and such low surface brightness that they verge on disappearance in ordinary imaging. Hubble observations of Leo 4, for example, show a star-starved dwarf galaxy whose identity depends on a sparse population of resolved stars rather than on any broad luminous body. Other newly studied candidates around the Milky Way are fainter still, with only a few dozen or few score visible stars in the available data. In these cases, the object lives near the threshold where the sky can still yield a coherent pattern at all, because the light is so weak. The apparent brightness of an ultra-faint galaxy does not scale in a simple way with distance alone. A nearby system may still escape notice if its stars are too dispersed. A somewhat farther one may be found if chance places it in a clean region of sky, and if its stellar concentration is slightly more favourable. Detection depends on a delicate balance among luminosity, size, foreground contamination, and survey depth. Low surface brightness is therefore not an incidental property. It is the central observational reason these systems remain concealed. It defines the barrier between what belongs to the known Milky Way satellite population and what likely exists just beneath present limits. The same property creates uncertainty in measurement after discovery. When a galaxy's visible boundary is weak, its size can be hard to estimate. When the total number of detected stars is small, the total luminosity carries large uncertainty. When member stars are sparse, contamination from unrelated foreground stars can alter the inferred shape or significance of the system. Barely visible light therefore affects not only whether a galaxy is found, but also how confidently it is characterized. It turns every stage of study into an exercise in careful inference. The galaxy is real, yet much of what is claimed about it must be extracted from limited visible evidence. Around the Milky Way, the hidden ultra-faint galaxies are thus concealed by the physics of distribution more than by the physics of emission. Their stars shine in ordinary ways. The concealment comes from how little stellar light exists and how widely that light is spread. They're not dark in the strict sense, they are diluted. Their surface brightness falls so low that even nearby systems can sink beneath the ordinary brightness of the sky. In this region of the story, the hidden satellites are defined first by light that almost fails to gather. They are galaxies whose existence can persist clearly in gravity, while remaining only barely present in sight. An ultra-faint galaxy does not usually present a strong outline. It does not rise from the sky with a sharp rim, a bright center, or a clear internal pattern. Its shape is instead weakly held in view, defined by a small number of stars spread across a surprisingly broad area. This diffuse structure is one of its most important features. It means that the visible body of the galaxy is loose rather than dense, even when the object is real and gravitationally bound. Its starlight does not gather itself into a concentrated form. The galaxy appears light in content and soft in boundary, as though it has only barely assembled enough visible matter to draw a shape at all. This is why ultra-faint systems are often described as dwarf spheroidal in appearance. The term means that they tend to lack the flat disks, arms, lanes, and bright knots seen in larger star-forming galaxies. They usually look simple, rounded, or gently elongated, with no obvious internal ornament. Yet even this description can sound firmer than the data truly are. In many cases, the visible structure is so sparse that the apparent form depends strongly on which stars are judged to belong to the system. A galaxy may look round in one rendering and slightly stretched in another, not because the object itself changes, but because so few stars define its body that small differences in membership can alter the impression of shape. The diffuse nature of these galaxies becomes clearer when astronomers describe their size through the half-light radius. This is the radius that encloses half of the galaxy's total light. It is a practical measure because many ultra-faint systems have no sharp visible edge. Their stars simply thin outward until the system blends into the surrounding field. The half-light radius therefore provides a way to describe scale without pretending that the galaxy ends at a bright and obvious boundary. For ultra-faint satellites, this radius can be surprisingly large compared with the tiny amount of visible light they contain. That contrast is central to their character. They are not only faint, they are faint while also being physically extended. This combination makes them look fragile. A compact cluster of stars can carry a modest total luminosity and still stand out because the stars are crowded together. An ultra-faint galaxy can have a similar or even lower luminosity while occupying a much larger region. The visible stars are then too spread out to create any strong core. The galaxy becomes a loose stellar configuration, a pattern of low density rather than a bright object. Recent census work on Milky Way satellites treats structure in exactly these terms. Scanning for systems across a wide range of half-light radii and using size as one of the key ways to distinguish likely galaxies from more compact stellar systems. In this structural sense, diffuseness is not a secondary trait. It is one of the main signs that a faint system belongs to the galaxy population rather than to the denser family of clusters. Even so, the distinction is not always clean. At the smallest and faintest end, some Milky Way companions occupy a difficult middle ground. A star cluster is typically more compact. An ultra-faint galaxy is usually more extended, but nature does not place a hard visible border between them. Some candidate systems are so compact and so poor in visible stars that their classification remains uncertain. Others are clearly more diffuse, and therefore easier to treat as galaxies in structural terms, even before detailed motion or chemical measurements are added. The problem is not that astronomers do not know what a shape is. The problem is that these systems sometimes contain so little visible structure that size itself must be inferred from very limited evidence. This evidence is often modelled with simple mathematical profiles that describe how stars are distributed from the centre outward. In practice, astronomers commonly fit smooth profiles such as a plumiform to the star counts. This does not mean that the galaxies are known in exquisite detail. It means that a simple, idealized distribution helps measure a weak and noisy structure. The resulting shape is often treated as approximately elliptical, with a half-light radius, an ellipticity, and a position angle. These terms give a language for describing a system that may contain only a small visible population. Ellipticity indicates how stretched the galaxy appears. Position angle indicates the direction of that stretch on the sky. Such parameters lend order to the data, but they do not remove the essential fact that the galaxy remains structurally delicate in appearance. A diffuse stellar shape also means that the galaxy is read statistically rather than visually. There may be no unmistakable center that the eye can immediately fix upon. Instead, the center is estimated from the distribution of member stars. There may be no crisp fall-off that marks the edge. Instead, the density of stars fades gradually into the background. There may be no richly populated interior to stabilize the impression of form. Instead, the form is carried by a sparse and fluctuating set of stars, any one of which may matter disproportionately in the measured structure. In a brighter galaxy, one missing or misidentified star changes little. In an ultra-faint dwarf, a few such changes can alter the inferred size, roundness, or concentration in a noticeable way. This is what makes these galaxies seem both present and insubstantial. They occupy real space, often across tens or hundreds of light years, yet their visible bodies can be built from astonishingly few detectable stars. Leo IV, described by NASA as a small and faint star-starved dwarf galaxy, illustrates the general impression well. The system exists clearly enough to study, yet its appearance is never one of abundance. Other recently discussed candidates are even more austere, with only a few score visible stars. In such cases, the galaxy's shape is barely more than a low-density stellar arrangement, a broad and soft figure drawn with very little material. Around the Milky Way, these diffuse stellar shapes define the ultra-faint population at the level of form. They show galaxies reduced almost to outline alone. No arms emerge. No bright central mass announces itself. No rich stellar body fills the interior. Instead, there is a thin configuration of old-looking stars, spread wide enough to make the object structurally gentle and observationally elusive at the same time. The galaxy becomes a kind of minimum visible architecture, a system that still possesses spatial extent and coherent form. yet does so with so little light and so little concentration that its shape appears more like a whisper than a structure. When the visible structure of an ultra-faint galaxy is reduced to a sparse gathering of stars, the age of those stars becomes one of the clearest ways to understand the system. In many of the Milky Way's hidden ultra-faint galaxies, the stellar population is overwhelmingly ancient. These are not places where bright young stars shine in large numbers, or where recent stellar birth changes the appearance of the galaxy from one era to the next. They are systems whose visible light comes mainly from stars that have endured for almost the entire history of the universe. Their starlight is quiet because it comes from long-lived stars, not from youthful brilliance. In this sense, the galaxies appear faint not only because they contain few stars, but also because the stars they do contain belong mostly to great age. Astronomers determine this age by studying how stars of different brightness and colour are distributed within the galaxy. A star's colour gives a clue to its temperature, and its brightness helps indicate where it stands in its life cycle. When many stars in one system are plotted together, they form a pattern that can be compared with models of stellar evolution. In ultra-faint galaxies, that pattern often reveals a population dominated by old, low-mass stars, together with red giant stars that represent a later stage in the lives of stars born long ago. What is often missing is just as important. There is little sign of the hot, luminous blue stars that would point to recent star formation. The galaxy therefore reads as an ancient stellar community, one whose visible members mostly belong to a very early chapter of cosmic history. This conclusion becomes especially strong when observations reach the faint main sequence stars, the long-lived stars that remain in the stable middle phase of their existence. The point at which stars begin to leave that sequence and become red giants provides a sensitive clock. In several ultra-faint galaxies studied with Hubble, including Leo 4, the stars appear more than 13 billion years old. That places them among the oldest known stellar populations in the nearby universe. Their ages cluster so closely that astronomers infer not only great antiquity, but also a brief and early period of star formation. These galaxies do not seem to have formed stars steadily across cosmic time. They appear to have formed most of their visible stellar population early, and then remained largely unchanged in that respect for the vast remainder of their existence. The impression this creates is one of stillness. A larger galaxy often contains stars of many ages. Some are ancient, some are middle-aged, some are newly formed and still bright with youthful heat. Such a mix gives a galaxy a layered and ongoing character. Ultra-faint dwarfs often lack that layered variety. Their stars resemble an old surviving remnant rather than a continually renewed society. Many of the visible members are small, dim stars whose slow evolution allows them to persist for billions of years. Red giant stars appear as brighter markers of the same old population, helping to reveal the system at all, but the dominant impression is that the galaxy is lit by survivors. The stars present now are those that formed early and endured because their masses are low enough for long lifetimes. This ancient character helps explain why these galaxies can preserve such a simple, visible appearance. A young stellar population usually brings strong contrast. Massive young stars are bright, blue, and short-lived. They reshape the light of a galaxy quickly. Ancient populations do not. They produce a softer and more subdued luminosity, dominated by lower mass stars and by giants that stand out only because most of the rest are so faint. The galaxy therefore appears old in a visual sense as well as in a chronological one. Its light has little urgency. It carries none of the bright signs of recent growth. It seems settled into a long afterlife, where visible change proceeds only through the slow evolution of stars born near the beginning. The age distribution also tells something about the scale of these systems. In a more massive galaxy, repeated waves of star formation can occur because enough gas, structure, and internal protection remain to support a long and varied stellar history. In an ultra-faint galaxy, the visible record often suggests the opposite. The star formation history appears short and early. Once that first small generation of stars forms, little or nothing seems to follow. The population then ages together. Over billions of years, the most massive stars die away, leaving behind the long-lived stars that now define the galaxy's faint body. What remains visible in the present is therefore not a full cross-section of all stellar ages, but a narrow population shaped by endurance. This is why ancient stellar populations are so important in the study of hidden satellites around the Milky Way. They make these galaxies more than merely small. They make them old in a nearly primordial sense. Observations indicate that some are relic systems whose stars formed very early, perhaps before many larger galaxies had reached their later complexity. The phrase fossil galaxy is sometimes used in this context, not to suggest that the system is dead in an absolute way, but to indicate that its stellar population preserves an early state with relatively little later alteration. The stars then serve as a surviving record of an epoch when galaxy formation operates on much smaller scales and under harsher cosmic conditions than in the present universe. Even within this oldness, there can still be subtle variety. Not every ultra-faint galaxy is identical in its exact star formation history, and uncertainties remain for the faintest candidates, where only a small number of stars are measured. Some systems are better observed than others. Some retain clearer stellar sequences than others, yet the broad pattern is strong. The known ultra-faint satellites of the Milky Way are dominated by old stars, usually older than 10 billion years and often older than 13 billion years in the best-studied cases. This shared antiquity gives the population a remarkable coherence. Across many separate systems, spread through the halo, the same quiet message appears in the starlight. Around the Milky Way, these hidden galaxies therefore carry ancient stellar populations as one of their deepest signatures. Their stars do not speak of recent formation, rich renewal, or ongoing change. They speak of a remote beginning and a long survival. The galaxies remain visible now because small, durable stars continue to shine after immense spans of time, while a few red giants make the population easier to trace. The overall effect is austere and calm. These are not lively stellar systems in the present age. They are old gatherings of light, composed largely of stars that have persisted since near the dawn of galaxy formation, and that still mark, in their faint and patient glow, the early history of the Milky Way's hidden companions. The stars in ultra-faint galaxies do not only reveal great age, they also reveal chemical simplicity. In astronomy, elements heavier than hydrogen and helium are often grouped together under the convenient name metals. The word does not mean only iron or familiar solid substances. It refers broadly to the heavier elements built inside stars and spread outward when stars die. A galaxy that has passed through many generations of star formation usually becomes richer in these heavier elements over time. Its gas is gradually enriched. New stars then form from material that has already been processed by earlier stars. In the hidden, ultra-faint galaxies around the Milky Way, that long chemical layering usually does not appear. Their stars often contain remarkably small amounts of heavy elements, as though the galaxies take part in only the earliest and most limited stages of enrichment. This makes their starlight chemically poor in a very specific sense. The stars do not lack matter, they are made of ordinary stellar material, but compared with stars like the Sun, many stars in ultra-faint galaxies contain far less iron, calcium, and other heavy elements. Spectroscopic studies, which separate starlight into its component wavelengths, show that these galaxies host some of the most metal-poor stellar populations known. Review work on ultra-faint dwarfs describes them as among the least chemically evolved stellar systems in existence. That description matters because it places them close to the beginning of chemical history. Their visible stars preserve a record from a time when the universe has not yet been extensively reworked by repeated stellar generations. Chemical simplicity also fits naturally with their faintness and age. A galaxy that forms only a small number of stars early on will produce only a small number of stellar explosions and only a limited release of newly made heavy elements. If later star formation does not continue, then there is little chance for repeated enrichment. The system remains chemically primitive. Its stars retain the signature of gas that has been touched by only a few early events, and in some cases perhaps by very few indeed. The heavy elements are present, but at extremely low levels. The galaxy therefore does not merely look simple in shape. It is simple in chemical history as well. This simplicity, however, is not the same as perfect uniformity. Ultra-faint galaxies often contain only a tiny visible population, but even within that small population, astronomers can detect a spread in chemical abundances. Some stars are poorer in heavy elements than others. This suggests that the system does not form all of its stars from one perfectly mixed cloud. Instead, a few early episodes of enrichment likely occur, and the resulting material does not become evenly distributed before later stars form. In larger galaxies, repeated star formation and larger gas reservoirs encourage more mixing and more chemical smoothing. In ultra-faint dwarfs, the process can remain patchy. A small number of events leaves an uneven imprint. The galaxy is chemically simple overall, yet internally it can still preserve the record of incomplete mixing. This kind of abundant spread is important because it distinguishes a galaxy from a simple star cluster. In a cluster, stars usually form together from one chemically well-mixed cloud and therefore share nearly the same heavy element content. In an ultra-faint galaxy, the situation is often broader and messier. The stars may still be very old, but they do not always carry identical chemical signatures. That variation suggests an environment capable of retaining at least some ejecta from early stellar deaths, and of forming stars over more than one brief episode. Even when the total visible population is tiny, the chemistry can reveal that the system has a galactic history rather than a single compact birth. In this way, chemical simplicity helps define the galaxy, while chemical variation helps confirm it. The low heavy element content also gives these galaxies unusual importance in the study of the early universe. Stars with extremely little enrichment are valuable because they preserve conditions closer to primordial matter. They do not contain pure hydrogen and helium, since some heavier elements are already present, but they come closer to the chemical beginning than stars formed later in richer environments. Some stars in ultra-faint dwarfs reach extremely metal-poor levels, among the lowest measured in any galactic system. This suggests that the galaxies have experienced only minimal chemical processing since their formation. Their stars therefore serve as surviving archives of early nucleosynthesis, the production of new elements inside the first generations of stars and their explosive deaths. At the same time, the pattern of element ratios can carry finer clues. Some heavy elements are mainly produced in ordinary core collapse supernovae, the deaths of massive stars. Others arise from rarer processes such as the rapid capture of neutrons in violent events. In several ultra-faint galaxies, astronomers find very little enrichment of many heavy elements overall, consistent with only a few early sources. In a few special systems, unusual enhancement of certain neutron capture elements suggests that one rare event may leave a dramatic chemical mark on a very small galaxy. That possibility does not remove the broader simplicity, it reinforces it. In a chemically tiny system, a single enrichment episode can matter enormously because there are so few stars and so little gas to dilute its products. The galaxy becomes a place where rare chemical events remain visible with unusual clarity. This chemical poverty also implies weakness in self-enrichment. A more massive galaxy can better hold on to gas and enriched material after stellar explosions. An ultra-faint galaxy has much less visible mass and a much shallower ordinary baryonic reservoir. The ejecta from a few early supernovae may escape easily or disperse unevenly. Later star formation then either stops entirely or continues in only a very limited way. The result is a system that never climbs far up the chemical ladder. It remains poor in heavy elements not because chemistry fails, but because the scale is too small for long enrichment to proceed efficiently. The galaxy begins with little, processes little, retains only part of what it makes, and then often falls silent. This is why chemical simplicity is one of the strongest signatures of the Milky Way's hidden, ultra-faint galaxies. Their stars are old, but not merely old. They are old and poor in heavy elements, preserving a record of short and limited early evolution. Their chemistry indicates that only a few stellar generations shape the visible system before the process largely halts. Within their sparse stellar populations, small abundance spreads hint at incomplete mixing and minimal self-enrichment, while the overall poverty of metals marks them as among the least chemically evolved galaxies known. In these faint companions, the history of matter remains close to its early form. The stars still carry, in their austere compositions, the memory of galaxies that begin small, enrich briefly, and then remain chemically simple for almost all of cosmic time. After the old stars and their chemical poverty are understood, another striking feature of the Milky Way's ultra-faint galaxies comes into view. These systems are quiet not only because their stars are ancient, they are quiet because they possess little gas and often almost no detectable gas at all. In astronomy, gas is the raw material from which new stars form. A galaxy rich in cold gas can continue to build fresh stellar populations over time. A galaxy poor in gas cannot do so easily. In the hidden ultra-faint satellites around the Milky Way, this lack of material is one of the clearest reasons their visible history seems to stop so early. The galaxies do not simply grow old, they lose, exhaust, or fail to retain the substance needed for renewal. This absence is especially important because gas is normally one of the defining ingredients of galactic life. In larger galaxies, clouds of hydrogen drift through disks and halos, cool in dense regions, and collapse under gravity into new stars. Such a process gives a galaxy an ongoing rhythm. Bright young stars appear, heavy elements increase, light changes, internal structure becomes layered by age. Ultra-faint dwarf galaxies usually do not show this rhythm in the present era. Their known stars belong mostly to the deep past, while the medium required for later star formation is either missing or present at levels too low to sustain much visible activity. The galaxy then appears not merely old, but dormant. This dormancy is most evident in the dwarf spheroidal companions of the Milky Way. the broad family to which many ultra-faint systems belong. These galaxies are typically gas-poor compared with dwarf irregular galaxies found in more isolated environments. The contrast suggests that environment matters. A small galaxy moving within the halo of a massive host like the Milky Way does not keep its gas as easily as a more isolated dwarf does. The gas can be stripped by motion through the hot halo medium of the larger galaxy, pulled away by tidal influence, heated so that it no longer cools efficiently, or gradually lost after the energy released by early stellar explosions. For an ultra-faint system with only a tiny visible mass, each of these processes can matter strongly. The galaxy does not need to endure a dramatic catastrophe. Even modest losses may be enough to leave it permanently gas-poor. In such a system, the early period of star formation can be brief. A small amount of gas gathers, stars form. Some of the more massive among them live quickly and die in powerful explosions. Those explosions inject energy into the remaining gas. In a deep and massive galaxy, much of that gas may stay bound, cool again, and support later generations of stars. In an ultra-faint dwarf, the visible body is too slight for that resilience. The gas may be pushed outward, heated, or dispersed beyond easy recovery. Once that happens, the stellar record becomes effectively closed. The stars already formed remain. New ones scarcely follow. The galaxy enters a long era of silence. This silence does not mean absolute inactivity in every physical sense. Stars continue their own slow evolution. Red giants age. Faint stars persist. Orbits continue. Gravity still shapes the system. Yet at the level of star formation, the galaxy becomes nearly still. It no longer transforms gas into new light in any substantial way. The absence of blue young stars reflects this condition clearly. So does the dominance of old stellar populations in color magnitude diagrams. The visible galaxy then becomes a remnant of one early productive phase, followed by immense duration with little visible change. Its present appearance is therefore not the result of continuous life, but of early formation followed by near-complete quiescence. This helps explain why ultra-faint galaxies seem so austere. They do not contain obvious nebulae lit by newborn stars. They do not show bright associations of hot young stars. They do not display the layered texture of systems that continue forming stars over billions of years. Instead, the light is produced by an old population that remains after the gas-driven phase has ended. The galaxy looks thin because it has not been replenished. It looks chemically simple because there have been few opportunities for repeated enrichment. It looks ancient because nothing significant in its stellar population has been added for an immense span of time. Missing gas and halted star formation therefore shape nearly every visible trait. The loss of gas also interacts with scale in a decisive way. A larger galaxy can absorb disturbances and still retain enough material to recover. An ultra-faint one operates much closer to the threshold of failure. It begins with only a small reservoir. It forms only a limited number of stars. It has little ordinary matter to hold the remaining gas in place. Once the balance tips, the path back to active star formation becomes narrow or impossible. This is why many ultra-faint satellites appear to preserve only one dominant old stellar episode. The systems are so small that silence arrives early and then lasts. Observations indicate that this early shutdown may occur in more than one way. Internal feedback from the first stars can help remove gas. The environment of the Milky Way can strip or heat what remains. The rising radiation background in the early universe may also make it harder for tiny systems to cool and retain gas after the first period of star formation. It remains uncertain how strongly each process contributes in every individual galaxy, and the balance may differ from system to system, yet the shared outcome is plain enough. The gas largely disappears, and the visible history of star formation becomes short. Across many ultra-faint satellites, the same pattern returns: a small beginning, followed by long dormancy. This dormancy also deepens the impression that these galaxies are relics. They're not merely faint objects surviving in the halo. They are systems whose star-making life appears to have ended near the beginning. What remains today is a lingering visible body composed of stars that formed when gas is still available, and conditions still allow collapse. Once that window closes, the galaxy persists in a subdued state. It continues as a bound stellar system, but not as an active nursery of new light. The silence is therefore one of the clearest ways these galaxies preserve the past. Their stillness reflects not only age, but also the disappearance of the medium that would have allowed later change. Around the Milky Way, the hidden ultra-faint galaxies thus carry a powerful absence within them. They are missing the gas that could have sustained renewal. Their stars show that formation once occurs, but only briefly. After that, the systems settle into prolonged quiet. The visible galaxy becomes the residue of an early beginning, not the product of continual growth. In this region of the story, the hidden satellites are defined by what is no longer there. Their silence is the consequence of missing gas, and their ancient light endures because the active phase of star formation fades away long ago and never truly returns. At the visible level, ultra-faint galaxies seem almost empty. They contain very few stars, little or no gas, and only the weakest trace of gathered light. Yet when astronomers study how the stars move inside these systems, a deeper picture appears. The visible matter does not seem sufficient to hold the galaxy together on its own. The stars move as though they are embedded in a much larger unseen mass. This is the basis for saying that ultra-faint galaxies are dominated by dark matter. The claim does not arise from imagination or from the mere wish to place invisible substance into every faint object. It arises because the observed starlight accounts for too little gravitational pull to explain the motions that the stars actually show. The key evidence comes from stellar kinematics, the measurement of stellar motion. In practice, astronomers usually observe the line-of-sight velocities of member stars. This means they measure how quickly each star moves toward or away from Earth. Even in a tiny galaxy with only a small number of observable stars, these measurements can reveal a velocity dispersion, a spread of stellar speeds around the average motion of the system. If the galaxy contained only its visible stars and almost no other mass, that dispersion would usually be expected to remain smaller. In many ultra-faint dwarfs, however, the measured spread is too large for the luminous matter alone. The stars appear to be moving under the pull of something much more massive than the faint stellar body suggests. This is a subtle argument, but a powerful one. Dark matter is not seen directly in these galaxies. No telescope captures a glowing halo around the stars. Instead, the unseen mass is inferred from gravity. The principle is simple. Faster internal motion requires stronger gravitational binding if the system is to remain intact. When the visible stars do not provide enough mass for that binding, an additional component is inferred. In the Milky Way's ultra-faint satellites, that inferred component is often dominant by a very wide margin. Review work on these systems describes them as the most dark matter-dominated galaxies known. The visible galaxy is therefore only a thin, luminous tracer moving inside a much larger invisible halo. This conclusion becomes especially striking when astronomers compare mass with light. A mass-to-light ratio asks how much matter is present for a given amount of luminosity. In the Sun, mass and light belong to the same object, so the ratio is familiar in a straightforward way. In a galaxy, the ratio can grow much larger if most of the matter is not luminous. In ultra-faint dwarfs, the ratio is often enormous. For some systems, it reaches many hundreds of times what would be expected from stars alone within the half-light radius, and in a few, especially extreme or uncertain cases, the inferred value rises still higher. Such numbers do not mean that every measurement is equally secure, but they do mean that the ordinary stellar population cannot plausibly account for the total binding mass. Light becomes only a very small fraction of the whole. This is one of the main reasons these systems are classified as galaxies rather than star clusters. A star cluster is made mostly of stars. Its gravity is largely the gravity of the stars themselves. In an ultra-faint galaxy, the situation appears different. The stars are too few and too faint to explain the observed internal motions. The system behaves as though it lives inside a dark matter halo. This inference is strengthened by the chemical abundance spreads discussed earlier. Together, the dynamical evidence and the chemical evidence show that an ultra-faint dwarf is not merely a loose cluster. It is a true galactic system, one in which visible stars occupy only a tiny fraction of the total mass budget. Astronomers remain careful in how they make this inference because the measurements are difficult. These galaxies are faint precisely because they contain so few bright member stars. A velocity dispersion derived from a small sample can be distorted by foreground contamination, by measurement uncertainty, or by unresolved binary stars whose orbital motion alters the observed speed of an individual star. Some systems are also affected by tides from the Milky Way, which can complicate the assumption that the stars are in simple dynamical equilibrium. Yet modern review work finds that in most cases the measured dispersions are robust enough that the dark matter conclusion remains strong. The details of each halo may still be uncertain, but the broad dominance of unseen mass persists across the known population. This does not mean every candidate system is settled beyond dispute. At the faintest edge, some objects remain ambiguous. A handful of recently studied systems sit so close to the boundary between galaxy and cluster that the available kinematic data do not yet compel a final classification. In such cases, astronomers weigh size, chemistry, and motion together. A structurally compact object with limited abundance information and uncertain dispersion may remain unresolved for some time, but these edge cases do not erase the wider pattern. The established ultra-faint dwarfs around the Milky Way overwhelmingly point in the same direction. Their visible bodies are too slight for the gravity they seem to require. Dark matter dominance also explains why these galaxies matter so much beyond their own scale. Because their visible content is so small, the usual complicating effects of gas, recent star formation, and strong internal feedback are reduced compared with larger galaxies. The stellar component acts like a sparse set of test particles tracing the central part of a dark halo. In that sense, ultra-faint dwarfs become unusually clean laboratories for studying dark matter on small scales. Their very poverty of ordinary matter becomes scientifically useful. The less luminous complexity they contain, the more directly their internal motions speak about the unseen mass that surrounds them. This unseen mass does not make the galaxies bright, rich, or visually impressive. It does something quieter. It allows a tiny and ancient stellar population to remain gathered as a galaxy at all, without such a dominant invisible halo. Many ultra-faint systems would not appear able to hold together in the way their measured stars suggest. The stars would represent too little gravity for the observed structure and motion. Dark matter therefore operates here not as an added curiosity, but as the main gravitational framework. The luminous body is almost a residue, a small visible frosting over a far deeper invisible foundation. Around the Milky Way, the hidden ultra-faint galaxies are thus defined by a paradox of appearance. They look like nearly empty systems, yet they behave like objects with much more mass than their starlight reveals. Their ancient stars drift within shallow, visible bodies, but the motions of those stars point to large dark halos beneath. This is why the galaxies remain central to modern astrophysics. They reduce the visible world almost to a minimum, while preserving strong gravitational evidence for the unseen. In these faint companions, dark matter dominance is not a secondary property. It is the main condition that allows the smallest galaxies to exist as galaxies at all. In the outer halo of the Milky Way, an ultra-faint galaxy does not rest in perfect isolation. It moves through the gravitational field of a far larger host. That movement gives rise to one of the most delicate features of these tiny systems, their orbits and their exposure to tides. In astronomy, a tidal force is the difference in gravitational pull across an object. The side nearer the Milky Way feels a slightly stronger pull than the side farther away. In a large and massive galaxy, that difference may do little more than shape the outer structure over long spans of time. In an ultra-faint dwarf, where the visible body is already sparse and the binding is delicate at the level of stars, tidal influence can become decisive. The galaxy remains a system of its own, but it does so under constant strain. An orbit in the halo is not a simple circle traced forever at one fixed distance. A satellite galaxy may follow an elongated path that brings it closer to the Milky Way at one stage and farther away at another. It may pass through regions where the host's pull changes significantly. It may also carry a long orbital period, requiring immense spans of time to complete a circuit. For an ultra-faint galaxy, the exact path matters because the strength of tidal stress depends on distance from the galactic center. Far out in the halo, the tide is weaker. Closer in, the differential pull becomes stronger. A small galaxy that repeatedly approaches the inner halo may therefore experience cumulative stripping and distortion over billions of years. This process does not necessarily destroy the galaxy all at once. More often it begins subtly. The outermost stars are the least tightly bound and therefore the easiest to remove. As the satellite moves through the Milky Way's field, those stars can be pulled away first, especially near the points in the orbit where the host's tidal force is strongest. The central part of the galaxy may survive while the outskirts become depleted. Over time, the visible body can shrink, elongate, or develop irregular outer structure. In some cases, stars lost from the satellite stretch into tidal tails or streams, faint elongated features that mark the path of disruption. In other cases, the evidence is less dramatic and appears only as a weaker symmetry or a gradual imbalance in the stellar distribution. For ultra-faint systems, this matters because they begin so close to the edge of detectability. A larger galaxy can lose some outer material and remain obviously intact. A system built from very few visible stars has much less margin. The removal of even a modest number of stars can alter its measured size, luminosity, and apparent shape. Tidal stripping therefore affects not only the physical system, but also the way it enters the catalogue. A galaxy under tidal stress may look more elongated than it otherwise would. It may appear less luminous because some members have already been lost. It may even drift toward ambiguity, becoming harder to separate from a dissolving star cluster or from an unbound stellar remnant. This is why astronomers treat the internal motions of some satellites with caution. When a galaxy is in near equilibrium, meaning its stars move under a relatively stable balance between motion and gravity, the measured velocity dispersion can be used to infer the mass of the system, but tides can disturb that balance. If the Milky Way is actively pulling a satellite apart, some of the observed stellar motions may no longer reflect a simple bound structure. The interpretation of dark matter then becomes more complicated. It remains true that many ultra-faint dwarfs appear strongly dark matter-dominated, but for any individual system under significant tidal influence, the observed velocities must be considered carefully. A fragile orbit can blur the clean relation between motion and binding mass. The visible structure of some satellites supports the idea that tides are already shaping them. Elongation, irregular outskirts, or hints of associated stellar debris suggest that the Milky Way is not merely hosting these galaxies, but slowly working upon them. Yet the degree of disruption varies. Some ultra-faint galaxies appear comparatively regular, implying that they are either on gentler orbits, presently at larger distances, or protected by central dark matter concentrations strong enough to resist immediate destruction. Others appear more vulnerable. Their visible bodies seem stretched or unusually sparse in ways that invite the interpretation of ongoing tidal disturbance. It remains uncertain in several individual cases how much of the observed form is intrinsic and how much is produced by the orbit, but the general principle is secure. Small satellites in a massive halo are never free from tidal influence. The Milky Way halo itself contains many signs that such interactions have occurred repeatedly. Stellar streams arc across the sky as remnants of disrupted systems. Some come from star clusters, others come from dwarf galaxies whose identities are being dissolved into the larger galactic halo. The outer halo is therefore not merely a storage region for surviving companions. It is also a graveyard of former ones, a place where earlier satellites have been stretched into long traces of stars. Ultra-faint galaxies exist within this same environment. Their present survival does not guarantee permanent survival. They orbit within a host that can gradually unmake them. This gradual unmaking is important because it helps explain why the smallest satellites may be fewer and harder to recognize than the number of original dark matter subhalos might suggest. Some tiny galaxies may have been stripped so heavily that little visible structure remains. Others may have been fully disrupted and added to the stellar halo. What survives to be observed today is therefore a filtered population, composed of systems whose orbits, internal structure, and dark matter content allow them to endure at least to the present time. A fragile orbit does not merely threaten a galaxy. It helps decide whether that galaxy will continue to exist as a recognizable object. Even when a satellite survives, the orbit shapes its history. Repeated passes through stronger tidal regions can remove stars and perhaps gas, alter the measured half-light radius, and transform the visible appearance into something more diffuse or elongated. The galaxy then carries the mark of its path in its body. It is not only a small system in the halo, it is a small system that has been sculpted by motion through the halo. The orbit becomes part of the object's identity, written into the looseness of its outskirts and the vulnerability of its form. Around the Milky Way, the hidden ultra-faint galaxies thus live under persistent gravitational strain. Their paths through the halo are long and varied, and those paths expose them to tides that can strip, stretch, and sometimes erase them. They remain present as galaxies only so long as their internal binding, supported largely by dark matter, can resist the host's differential pull. In this region of the story, the satellites appear not as static points in space, but as frail companions in motion. each one moving through a giant gravitational field that steadily tests how much of a galaxy can remain when almost nothing visible is there to spare. Some of the Milky Way's hidden ultra-faint galaxies are studied as fossils of rionization. In this context, a fossil is not stone or preserved bone. It is a surviving system that retains the marks of a very early cosmic event. Reionization is the period in the young universe when the first generations of stars and galaxies fill space with energetic radiation that changes the state of intergalactic hydrogen, heating and ionizing much of the gas between galaxies. For the smallest galactic systems, this change may be decisive. Gas that might otherwise cool and fall inward becomes harder to keep, harder to compress, and harder to turn into later generations of stars. A tiny galaxy that begins to form before this event may therefore continue afterward, not as a growing system, but as a remnant whose visible stellar population is largely fixed from that early time. This idea fits naturally with what is seen in many ultra-faint dwarfs. Their stars are extremely old, their chemical histories are brief and poor in heavy elements, their gas is absent or nearly so. Their later star formation appears very limited or absent. Hubble studies of galaxies such as Leo 4 and others of similar kind find stellar populations older than 13 billion years, with ages so closely grouped that astronomers have proposed a global shutdown rather than a long internal fading. NASA's summary of these measurements states that the stars in 3 studied ultra-faint dwarfs are more than 13 billion years old, and suggests that a global event such as reionization shuts down star formation in them. More recent observational summaries describe newly studied ultra-faint systems as empty of gas and composed only of very old stars, reinforcing the picture of ancient galaxies whose active lives are cut short long ago. The fossil interpretation rests on a simple physical argument. A large galaxy has enough gravitational depth to continue gathering and cooling gas even in a harsher radiation background. A tiny one may not. Before reionization, small dark matter halos can begin to collect gas and form stars. After reionization raises the temperature and pressure of the surrounding medium, those same shallow wells may struggle to accrete new gas, or even to retain what remains. Star formation then ends early. The system does not vanish. Its stars stay bound if the halo is strong enough. But the visible history becomes frozen near the beginning. The galaxy continues forward in time, while still carrying the conditions of a much earlier era. In that sense, the fossil is not frozen matter. It is frozen galactic development. This is one reason ultra-faint galaxies matter far beyond the Milky Way halo. Their present stars are local, but their significance reaches back to the first billion years of cosmic history. Work on the stellar fossil record of local group dwarfs argues that the ancestors of the faintest ultra-faint galaxies are themselves tiny star-forming systems during reionization, producing faint ultraviolet light and contributing to the broader radiation budget of the early universe. That means the faint galaxies seen today are not only relics of suppression, they are also traces of the population that helps transform the universe in the first place. They stand at both ends of the story, first as small luminous contributors to early cosmic change, and later as diminished survivors whose visible bodies still record that change. The visible calm of these galaxies therefore reflects a very ancient interruption. Their stars form early, perhaps in a short burst or in a few closely spaced episodes, and then the process largely ceases. Over the immense time that follows, the stars simply age. Massive stars disappear. Small, long-lived stars remain. Red giants briefly brighten parts of the old population. But the galaxy never regains a rich reservoir of cold gas, and never builds the layered age structure common in larger systems. It carries forward one dominant early episode while the universe around it grows more complex. A fossil of reionization is thus a galaxy that remains present in the current age, while preserving a star formation history largely shaped by conditions near the dawn of galaxy assembly. Even so, astronomers are careful not to treat every ultra-faint satellite as an unquestioned fossil in exactly the same way. The broad picture is strong, but individual histories can be complicated. Environmental effects from the Milky Way itself can also remove gas and shut down star formation. Tides, ram pressure, and host-related heating may all matter after a satellite enters the halo of a massive galaxy. Earlier work comparing local group dwarf star formation histories notes this ambiguity directly, observing that environmental effects can blur the distinction between galaxies quenched mainly by reionization and galaxies quenched later by host influence. Some studies find only a subset of candidate fossil systems remain fully consistent with having formed the bulk of their stars before reionization once uncertainties are taken into account. That uncertainty does not weaken the fossil idea so much as refine it. Reionization need not be the only force acting, and it need not act with identical strength in every system. A very small galaxy may first be limited by the early radiation background and later be further shaped by the Milky Way environment. Another may preserve a cleaner early shutdown. The question is therefore often one of degree and dominance, not of absolute exclusivity. Observations indicate that many ultra-faint dwarfs are excellent fossil candidates because their ancient stars, lack of gas, and curtailed star formation fit the predicted outcomes so well. It remains uncertain whether every object at the faint edge belongs equally in that category, especially when classification, orbital history, or star formation timing are still under study. What makes the fossil interpretation so compelling is the smallness of the systems themselves. These galaxies seem to preserve an early threshold in galaxy formation, where only a little visible matter gathers before the surrounding universe changes state. Their stars then become a durable record of that threshold. In larger galaxies, later star formation can partly erase the sharpness of the earliest epoch. In ultra-faint dwarfs, very little later activity exists to blur the original signal. The galaxies are sparse enough, old enough, and quiet enough that the ancient interruption remains legible. Their visible bodies are almost entirely built from stars that survive from near the beginning, and that survival gives modern astronomy a rare local window into an otherwise remote era. Around the Milky Way, the hidden ultra-faint galaxies therefore appear as some of the quietest survivors of the early universe. They are not bright monuments to cosmic beginnings. They are minimal systems, dim and easily overlooked, whose value lies in how little later history they contain. Their stars suggest an origin in the young universe. Their silence suggests early quenching, and their persistence suggests that a tiny galaxy can endure for billions of years after its main formative phase ends. In this region of the story, the ultra-faint satellites become living fossils in the strict astronomical sense, present-day galaxies, whose ancient stellar bodies still preserve the imprint of reionization and of the first small steps by which galaxies begin to form. At the smallest scale of galaxy formation, the difference between a galaxy and no galaxy at all becomes very narrow. An ultra-faint dwarf does not represent a reduced version of a large galaxy in every respect. It represents a system close to the lower limit where visible galactic structure can still emerge. In this regime, a dark matter halo may exist and remain gravitationally real while producing little starlight or none at all. The hidden ultra-faint galaxies around the Milky Way are important because they show that star formation can occur in such tiny halos, but only barely. They're not examples of abundant success. They're examples of marginal success, where just enough ordinary matter gathers, cools, and forms stars for a visible galaxy to come into being. This threshold begins with the dark matter halo itself. A halo is a gravitationally bound concentration of matter that contains far more mass than the visible stars it may eventually host. In the early universe, countless halos form across a wide range of sizes, but a halo does not become a galaxy simply by existing. To produce stars, it must also gather ordinary matter, keep that matter from escaping too easily, and allow it to cool into denser regions. Cooling is crucial because hot gas resists collapse. Only when the gas loses enough energy can gravity draw it inward and compress it into clouds that form stars. In larger halos, this process is comparatively efficient. In the smallest ones, it is precarious from the beginning. For a tiny halo, the first difficulty is capture. The ordinary matter of the universe does not fall equally well into every gravitational well. Shallow wells struggle to hold gas, especially once the surrounding environment becomes hotter and more hostile. Even before later suppression is considered, a very small halo begins with limited capacity. It gathers less material, reaches lower densities, and remains more vulnerable to disturbance. The halo may be real as a dark structure, but its visible future is uncertain. Much depends on whether enough gas can settle into it early enough and deeply enough to begin star formation before the opportunity narrows. The next difficulty is cooling. Ordinary matter in the young universe can cool through specific physical channels, but those channels do not operate equally at all scales. A small halo may fail to bring gas to the temperatures and densities where efficient cooling takes hold. If the gas remains too warm or too diffuse, it does not condense into the dense clouds required for stars. The halo then remains dark in the visible sense. It exists as a gravitational object, but not as a galaxy illuminated by a stellar population. This is why the smallest scale of galaxy formation is not simply about counting halos. It is about identifying which halos cross the physical threshold where cooling and collapse truly begin. Ultra-faint galaxies appear to sit just above that threshold. Their visible populations are so small, their star formation histories so brief, and their chemical enrichment so limited that they seem to record the minimum conditions under which a galaxy can still form. They're not rich in gas, not structurally robust, and not chemically evolved. They show what happens when the process succeeds only once or only for a short interval. A little gas settles, a little cooling occurs, a small number of stars forms. The galaxy becomes visible, but only barely. In that sense, an ultra-faint dwarf is not a well-developed galaxy reduced in brightness. It is a galaxy that almost fails to form. This is why so many of their properties converge toward austerity. A minimal stellar population implies that very little gas ever reaches the state needed for sustained collapse. Ancient ages imply that the main visible success occurs early, before later conditions close the window. Low heavy element content implies that only a few stars live and die before the system falls quiet. Missing gas implies that the baryonic reservoir never becomes large or durable enough to support continued activity. Dark matter dominance implies that the visible component remains a very small tracer inside a much larger invisible halo. Each of these properties points toward the same conclusion. Ultra-faint dwarfs occupy the regime where galaxy formation is possible, but only just. This threshold perspective also changes the meaning of absence. When astronomers say that many small dark matter subhalos may contain no stars, they're not saying that something has gone wrong in every case. They are saying that halo formation and galaxy formation are not identical processes. Below a certain scale, visible formation becomes inefficient or stops altogether. A halo may remain dark because it never collects enough gas, because its gas never cools sufficiently, because early heating removes the gas, or because the first brief attempt at star formation disrupts what little ordinary matter is present. The ultra-faint galaxies are therefore valuable not only for what they are, but also for what lies just beneath them, a likely population of even smaller halos that never become luminous galaxies at all. This makes ultra-faint dwarfs a natural boundary population. They define the transition between the visible and the invisible on galactic scales. Above them lie galaxies that form more stars, retain more gas, and build more extended histories. At their level, the visible record grows thin, old, and chemically simple. Just below them, the universe may contain structures that remain almost entirely dark. The ultra-faint galaxies therefore show where ordinary matter still manages to leave a lasting luminous mark inside the smallest known galactic systems. They are the last quiet rung before the ladder of visible galaxy formation fades into darkness. Because they sit so close to this limit, tiny differences in early conditions may matter enormously. A slightly deeper halo, a slightly earlier accumulation of gas, a slightly calmer local environment, or a slightly better capacity to retain heated material may allow one system to form a modest ancient stellar population, while another nearly identical halo remains dark. The difference between an ultra-faint dwarf and an invisible subhalo may therefore depend on narrow margins. This is one reason the faintest galaxies are scientifically powerful. They bring galaxy formation down to the scale where success is contingent, where the minimum physical requirements are exposed, and where the universe reveals that not every gravitational structure earns visible starlight. Around the Milky Way, the hidden ultra-faint galaxies thus mark the smallest scale at which galaxy formation still leaves a readable stellar body. They are not abundant luminous systems reduced to miniature size. They are threshold objects, formed in tiny halos where the ordinary matter only barely manages to gather, cool, and ignite. Their visible stars are the outcome of a narrow victory over failure. In this region of the story, the Milky Way's faintest companions show that a galaxy can exist with astonishingly little light, but they also show how close nature comes, at the smallest scales, to producing dark halos with no stars at all. The missing satellites puzzle begins with a mismatch in counting. In the standard picture of structure formation, dark matter gathers hierarchically, which means large halos grow by absorbing smaller ones and by being surrounded by many lesser subhalos. For a galaxy like the Milky Way, this picture predicts a rich swarm of small dark matter structures in the halo. Yet for many years, the number of known satellite galaxies is far smaller than the number of expected subhalos. The puzzle is not that galaxies fail to orbit the Milky Way at all. The puzzle is that visible companions seem too few when set beside the abundance of small structures predicted by the cold dark matter framework. At first, the discrepancy appears simple. Theory predicts many small companions, while observation finds only a modest set. But the puzzle changes as the observations improve. Once wide digital surveys begin to reveal ultra-faint dwarfs around the Milky Way, the known satellite count rises quickly. Systems once thought too dim to notice begin entering the census. The discovery of these faint companions shows that the original comparison is incomplete. because it is based on an observed sample limited by the brightness, size, and location of the objects that surveys can detect. The puzzle therefore shifts from a crude shortage of satellites to a subtler question about how many luminous satellites should truly be visible once the search limits are treated honestly. This is where completeness becomes central. A census of Milky Way satellites cannot be read as though the whole sky is searched equally, and as though every faint galaxy above the horizon would naturally announce itself. The faintest satellites are diffuse, low in surface brightness, and often hidden behind foreground confusion or outside the deepest footprints. Recent census work that combines DES, DELV, and PAN-STARRS recovers 49 known satellites above a strict detection threshold across most of the high-latitude sky, then uses artificial satellite injections and forward modelling to estimate how many remain unseen. That analysis predicts a total population of about 265 Milky Way satellites within its stated luminosity, size, and distance range, implying that many companions are still hidden rather than absent. The missing satellites puzzle therefore becomes a puzzle about luminous failure, not necessarily about missing dark matter structure. A dark subhalo can exist without becoming a visible galaxy. For the smallest halos, star formation is extremely inefficient. Some may gather too little gas. Some may fail to cool that gas to the point where stars can form. Some may lose gas early through heating or environmental effects. In that case, the halo remains part of the Milky Way substructure, but contributes little or no starlight to the observed census. This interpretation has long been one of the main ways the puzzle is understood, not that the small structures do not form, but that many of them never become luminous satellites at all. Recent simulations strengthen this view by showing that many subhalos are effectively starless from the start. In one recent study of local group analogues, the majority of subhalos remain devoid of stars, and the work argues that rionization plays the dominant role by preventing sufficiently dense gas from cooling below the threshold needed for star formation. In that picture, many small halos are not stripped of a rich stellar population later, they simply never achieve one in the first place. This does not remove the existence of the underlying subhalos. It explains why the visible population of satellites can be far smaller than the full dark matter population surrounding a Milky Way-like host. Even so, the modern form of the puzzle is not fully settled. Some recent work argues that once baryonic physics, reionization, and selection effects are treated more realistically, the classical discrepancy for luminous satellites is greatly reduced and may be close to reconciliation. Other analyses still emphasize that the answer depends on the exact modeling choices, on how the Milky Way halo mass is estimated, and on how completeness corrections are performed at the faint end. The broad direction is clear, the original dramatic mismatch has softened. Yet the question has not vanished, because the smallest visible galaxies lie precisely where both theory and observation are most delicate. This makes the ultra-faint satellites especially important. They occupy the range where the census changes most rapidly as surveys improve, and where the distinction between a luminous galaxy and a dark halo becomes most physically meaningful. A brighter satellite is easier to include in any fair count. An ultra-faint dwarf may sit just above the observational threshold and just above the physical threshold for star formation. It therefore affects both sides of the puzzle at once. Discovering more such systems raises the observed tally, while studying their ages, gas loss, and dark matter content helps explain why so many other small halos may remain dark. The faintest satellites are not a minor correction. They are the place where the counting problem becomes astrophysical rather than merely numerical. The puzzle also resists any perfectly fixed answer because the Milky Way itself offers only one host system observed from within. Its sky is partly obscured by the galactic disk. Its total halo mass is not known with perfect precision. Its present-day satellite system reflects a particular history of accretion, disruption, and association, including the influence of the Large Magellanic Cloud and the selective survival of small companions. A count made around the Milky Way is therefore both cosmological and local. It tests general theory, but it also depends on the specific character of this one galaxy and on the incompleteness of the view from inside it. That is why the missing satellites puzzle persists as an active counting problem, even after many new discoveries. Around the Milky Way, the missing satellites puzzle is thus no longer a simple statement that theory predicts many dwarfs, while astronomers see only a handful. It is a more refined tension between predicted dark substructure, observed luminous satellites, and the imperfect window through which the faintest systems are found. Wide surveys have revealed that the known sample is incomplete. Completeness modelling suggests that many satellites remain hidden. Modern simulations suggest that many sub-halos may be intrinsically dark because star formation fails at the smallest scales. The puzzle therefore survives in a transformed form not as a crude contradiction, but as a careful effort to determine how many of the Milky Way's smallest companions shine faintly enough to be missed, and how many never shine at all. When the Milky Way is viewed through its hidden ultra-faint galaxies, the galaxy itself begins to look different. These tiny companions do not add much light to the halo. They do not dominate the mass of the local group, reshape the disk, or rival the great visible structure of the Milky Way. Yet they reveal something more subtle and in some ways more important. They show that the Milky Way is not only a bright spiral galaxy with a disk, a bulge, and a large dark halo. It is also the centre of a much quieter surrounding system, one that includes many small, ancient, and nearly invisible companions. The meaning of these galaxies lies therefore not in spectacle, but in what they disclose about the larger home they orbit. First, they show that the Milky Way grows by accumulation. The galaxy does not form only from one smooth cloud in one continuous process. Its outer regions preserve the evidence of repeated addition, streams in the halo, disrupted remnants, globular clusters with unusual histories, and surviving dwarf satellites all point toward a long history of accretion. The ultra-faint galaxies extend this history to the smallest visible scale. They show that the Milky Way's growth includes not only the capture of larger companions, but also the retention and partial destruction of extremely small ones. The galaxy is therefore surrounded by a faint population that records how structure builds from the bottom upward, through the gathering of lesser systems into larger wholes. Second, these galaxies reveal that the Milky Way's halo is richer and more layered than its visible brightness suggests. A person looking only at the sky might imagine the Milky Way as a narrow river of stars across darkness. Modern astronomy reveals something much broader. Around that bright band lies a vast halo of dark matter, ancient stars, streams, clusters, hot gas, and faint satellites. The ultra-faint galaxies belong to this extended environment. Their presence confirms that the Milky Way's true domain is not defined by the disk alone. The galaxy's influence extends far beyond the bright spiral plane, into a dim realm where its smallest companions move slowly through a mostly unseen gravitational field. In this way, the hidden satellites help redefine the scale and nature of the Milky Way itself. They also show that the Milky Way is still only partly known, even in its immediate neighbourhood. That is one of the most striking lessons. The hidden galaxies are not remote objects near the edge of the observable universe. They belong to the closest galactic environment around the Milky Way, yet many remain newly discovered, uncertain, or still unseen. This means that the local universe retains an unfinished inventory. The galaxy nearest to human study is accompanied by systems so faint that they continue to evade detection. The lesson is humbling. Familiarity with the Milky Way does not mean completeness of knowledge. Even nearby space contains structures that remain below ordinary visibility and just beyond current census. At the same time, these galaxies clarify the role of dark matter in shaping the Milky Way. The large dark halo of the galaxy is not understood only through the motion of stars in the disk or through the overall mass of the halo. It is also traced by the existence and behavior of tiny satellites. Ultra-faint dwarfs show that the Milky Way is embedded in a hierarchy of dark structures. Around the main halo lie smaller subhalos, some luminous, some perhaps wholly dark. The galaxies that do appear mark the places where visible matter manages to settle into some of those subhalos. Their motions, survival, and internal dynamics all reinforce the view that the Milky Way is a luminous center within a much larger invisible architecture. The smallest satellites make that architecture easier to test because they contain so little ordinary matter of their own. The hidden companions also reveal something about the Milky Way's past environment. Their stars suggest that many of them form early and then stop. Their gas disappears. Their visible evolution becomes very limited. This tells a story not only about the satellites, but also about the conditions surrounding the galaxy as it grows. The Milky Way does not simply host these systems passively. Its halo strips, heats, and stresses them. Its gravity shapes their paths. Its environment may help silence them after their brief early activity. The meaning of the ultra-faint population is therefore relational. These are not isolated miniatures floating freely in space. They are satellites whose histories are entangled with the Milky Way's own development. To study them is to study the effect of a great galaxy upon the smallest bodies that fall under its rule. They also set a lower boundary on what the Milky Way can host as a galaxy system. A large satellite such as the Large Magellanic Cloud is unmistakable. An ultra-faint dwarf is almost not there in visible light at all, yet it still survives as a galaxy. This means the Milky Way's family includes objects across an enormous range of scale, from prominent companions down to systems barely above the threshold of detectability and barely above the threshold of galaxy formation itself. That range matters because it shows the continuity of the galactic system. The Milky Way is not accompanied only by obvious neighbours. It is accompanied by a full hierarchy, including some of the smallest galactic bodies known. In a broader scientific sense, these galaxies help turn the Milky Way into a laboratory for cosmology. Because they are near, they can be studied star by star. Because they are simple, they preserve early conditions with relatively little later complication. Because they are dark matter dominated, they offer a testing ground for the behavior of matter on very small galactic scales. Because they are incomplete in census, they challenge astronomers to improve surveys and selection modelling. In all these ways, the hidden ultra-faint satellites convert the Milky Way from a single object of study into a local system through which deeper questions can be asked. The galaxy becomes a place where the universe's smallest successful galaxies can be examined in detail. There is also a quieter meaning. The existence of these companions changes the emotional scale of the Milky Way. The galaxy is often imagined in terms of its bright central splendour, its spiral arms, its nebulae, and its star clouds. The ultra-faint dwarfs add another aspect surrounding that splendor as an almost invisible company of ancient survivors, dim systems that form early, change little, and continue to orbit in silence. They make the Milky Way seem less solitary and more layered, not only bright at its center but accompanied at its edges by relics of its formation era. These galaxies are small, but they deepen the character of the whole. Around the Milky Way, the hidden ultra-faint galaxies therefore carry a meaning larger than themselves. They reveal unfinished discovery in the local universe, confirm the layered structure of the galactic halo, expose the importance of dark matter on the smallest visible scales, and preserve traces of the earlier stages of galaxy formation. They show that the Milky Way's true surroundings are older, quieter, and more crowded with faint companions than ordinary sight suggests. In the end, these nearly invisible galaxies do not merely circle the Milky Way. They help explain what kind of galaxy the Milky Way is. Far beyond the bright band of the Milky Way, the smallest companions continue their quiet paths through the halo. They give off little light. They hold few stars. They preserve no bright sign that would draw immediate attention from a casual eye. Yet they remain. In their faintness, they carry a record older than most visible structures in the galaxy's present sky. Their stars form early. Their gas fades. Their chemical histories remain sparse. Their shapes stay loose and fragile. Around them, the Milky Way extends its gravity across immense distances, holding them in a realm where survival depends on almost invisible balance. These galaxies do not speak through brilliance. They speak through persistence. They remain at the threshold where a galaxy can still exist with scarcely any light at all. They show that the local universe is quieter and more delicate than it first appears. Around the Milky Way, space is not empty after the bright disk fades. It remains inhabited by dim survivors, each one carrying the memory of an early beginning and a long stillness afterward. In this calm outer company, the galaxy appears larger, older, and more layered. Its halo becomes not only a region of dark matter and scattered stars, but also a place of ancient remnants. The smallest companions drift there with almost no visible weight, yet with deep meaning. They reveal how galaxies begin on the narrowest scale, how they fall silent, and how they continue long after their active lives are over. The hidden ultra-faint galaxies remain nearly invisible, but they are never empty of significance. They circle in darkness with their old stars intact, marking the faint edge of what a galaxy can be. Around the Milky Way, they endure as the softest lights in the nearest cosmic night,